Okay, as an introduction, like warm up, I'm gonna read the problem, and I already highlighted the given, okay, and included the information in the picture that you see. Remember that the main object here in the problem is the rock, okay, which is this one over here. Okay, so this problem is about a girl that is throwing the stone. It says with an initial velocity of 12 meters per second, so already as a part of my givens, at a downward angle of 45 degrees to the horizontal. I write it as a part of my givens. In an attempt to hit the block of wood, that is floating on the river below. If the stone is thrown from a height of 20 meters, that means that the bridge is 20 meters high, okay? And it just reaches the water when the block is 13 meters away from the bridge. And then the main question is, does the stone hit the block? And we wrote the given, okay? We can indicate the position of the girl, well, her hand, basically, in a Cartesian plane. And in that part, you will notice that we have the coordinates of the initial position, okay? Or the launching point of the problem. That's, this occurs right in the moment that the stone leaves her hand, okay? In that precise moment, the Cartesian plane is located. Here you see the stone. The stone is carrying an initial velocity that here is not written, but you know that is 12 meters per second. And that velocity is represented with a vector or an arrow that you see over there in this direction, okay? Wait. I'm working in this part, okay? So, and now you can see that the trajectory of the rock is gonna be like a parabola, okay? And I was telling you the other day in class, the stone could either reach the target or not. Those are the two possibilities, and we want to know if it's going to, okay? And I gave you a bunch of formulas, okay? And we're going to start. In this kind of problems, it is important that we start by getting the components of the initial velocity. That's what we're gonna do in this first place. So the first step will be get the components of the initial velocity. Okay, and because we're talking about components, we're talking about X component and Y component, okay? So we say initial velocity in X and initial velocity in Y, okay? These are the components X and Y for the initial velocity. And I gave you already the formulas. They're over here. Okay. So I think it's my mouse, the one that is, no, it's good. Anyway. So the initial velocity, you can see that you can get it with the cosine of the angle and the y with sine of the angle. So you can write the formulas as initial velocity, cosine of the angle, and initial velocity, sine of the angle. Now, I told you already that we're going to use these formulas every time we have an angle that is measured from the horizontal, just like we have in this particular problem. This angle is measured from the horizontal. The problem is telling you, okay? Angle of 45 to the horizontal it means that it was measured from the horizontal axis. So we can apply these two formulas. So we say initial velocity, that is 12 meters per second, times the cosine of 45, and 12 meters per second times sine of 45 to get the two components. Okay. So how much you got?
8.49.
8.49 meters per second. Both, okay? Both are the same because the angle is 49, is 45, which is half of 90. So the two components are going to be equal for this time. If the angle changes, the two components are going to change. But now let's analyze the direction, the direction of the vector. Here, I have my vector that is initial velocity. Espérense. There I have my vector that is initial velocity. Yes, Valeria?
Miss, the formula of the cos and sin is gonna be used only with an horizontal, right?
Exactly, only when it's a horizontal angle. The exercise will tell you if the angle is going to be measured from the horizontal or from vertical. If it's vertical, you're going to flip the trigonometric functions. So here we have the vector of the initial velocity. This vector, as you can see, is going, okay? This vector is going to the right or to the left?
To the right.
It's going to the right, so it's going to be positive in x, okay? And it's going down or it's going upward?
Down.
It's going down.
It's going down, so it's going to be negative for y. That's important because when we get the components, we need to include those signs, okay? So the x component will be positive and the y component will be negative, okay? So here, when we get the components, we're going to specify the signs. It is positive in x and it's gonna be negative in y because it's going downward. And this one is positive because it's going rightward, okay? And we indicate the direction of the component. That is very important. Now, for this kind of exercises, we're going to look for a final velocity, okay? Why the final velocity? Take a look. The problem is asking me to find the final position, okay? The final position in the formula, to find a final position in x, you need to know the time. The time is not given in the problem. Now, we can find the time in two different ways. You can find the time here with this equation, or you can find the time here with this equation, but this equation, the time is raised to the second power, and you have to do a big mess to get it, but still you can get it. Now, my recommendation is, because this formula for final velocity in y is easier to isolate the time, you're gonna use this one instead of the other one. Now, if you want to look like a pro and like to make a huge procedure and get the exact same answer, okay? Because the answer is not gonna change. You can use the other procedure, but it's gonna take longer. Remember that time matters. So my recommendation is, if you need to isolate the time, this is the equation to use because it's simpler, okay? Now, in this step, we're going to find the final velocity in y. The purpose is to get the time, okay? So I'm going to find final velocity in y to get the time. So we say, final velocity in y is equal to initial velocity sine of the angle plus gravity time, okay? We have this equation. Take a look over here. we have this equation over here, okay, that says that we can get BF. And we have this other equation over here also to get BF. The difference is that this one requires time and this one requires delta Y. Which one do we have? According to the given, which one do we have? The time or the velocity or the delta Y?
Delta Y.
Okay, so here, you don't need to do it, okay? You don't need to do it like in a step, but from here, from your givens, you can get delta Y by saying delta Y is equal to main equation for delta Y, that is final minus initial. Final, that is 0 meters, minus initial, that is 20 meters. So delta Y is equal to negative 20 meters. So take a look. Only from the given, we were able to get delta Y. Now, take a look. Now that we have delta Y, let's analyze the formulas that we have over here. If I need to get the time, I can use either of those two formulas, okay? That I highlight right now in this moment. Sorry. Sorry, I gotta call these people from the bank. They're so disrespectful. They call at any time. Okay, so to find the time, we need to have final velocity in Y, initial velocity, sine of the angle that we already have, and gravity. This one, I don't have it, okay? And this one, the time, I don't have it neither. If I use the second formula, I don't have this one. I do have the initial velocity, I do have gravity, and I do have delta Y. So the purpose will be to find delta Y. Once you find delta Y, you use this equation to isolate for the time. So I need to find BF. So BF Y, final velocity in Y, is equal to, it's the one that I already gave you isolated as square root of initial velocity in Y to the second power plus 2 times gravity delta Y. And here it is important that you write the symbols, okay? Initial velocity in Y, we got it as here, negative 8.49. So you will replace, but it's gonna give you positive in the end. Okay, now you will replace the value of gravity. I'm waiting for this to update. I will replace the value of the gravity that even if it's not written in the problem, even if it's not written in the problem, you know that is negative 9.81 meters per second square, okay? Remember, this gravity is not raised to the second power. And then the value of delta Y that we just got from the given. Right now, in this moment, we got delta Y as negative 20 meters. Okay, now in your calculator, you're gonna do this. The last part that you're gonna do is getting the square root. In your calculator, you will press the key minus. Sorry, you will start with the parentheses. Then press minus 8.49. Okay, close parenthesis square. plus 2 parentheses 1 times 2 times negative 9.81 times negative one more time and then 20. Once you have your answer, press key, the equal key, and then you will press square root of the key that says ands. This you will do it in your calculator. Okay, very good. Very good, Cabrera. Lisette, 21.55. If you get an answer different than that, let me know, okay? So I, after the class, can send you a video how to do it in your calculator. So 21.55, because this is final velocity in y is a velocity, the units are going to be meters per second. Okay, now we need to analyze. We need to analyze, and I need your attention in this particular moment. So this stone is gonna come here, and then here, and then here, and then we don't know, but it's probably gonna be here, okay? So vertically, where is the stone going? Is this stone going upward and to the right? Or is the stone coming downward and to the right?
Downward to the right.
Downward and to the right. So that's very important that you analyze the direction of the stone, okay? The stone is going downward and also to the right. And because we are getting the final velocity in y, or the vertical velocity, and we saw that vertically the stone is going down, okay? So we say, okay, the stone is going down, therefore the velocity is going to be negative because the stone is moving downward, and you will indicate the direction of the velocity. This is the first part of the problem. Now that we have the final velocity, it's important that you don't forget the sign. So I'm going to highlight the sign, because if you forget, you're going to have a negative time, and negative times are never good, okay? Remember, we cannot go back in time. So once we have the final velocity, we're going to do the next step. That is, we're going to find the time. Yes, Valeria?
Miss, in this exercise is obligatory to draw, right?
In the quiz or in the classwork, I will provide you with a picture, but yes, it is important that you put the information in the picture like I did here. As you can see, I included more information in the picture than the one that it was given. So more or less in that way is the way I want you guys to work, okay? From the given picture, make your own analysis with the givens and everything, but on the picture. Some other times, yes, you will have to draw, but most of the time I will provide you with a picture because it's better. And in that way, it's not gonna take more time. So talking about time, we need to get a time. So the original idea was you find the velocity to then isolate for the time. So we're gonna use this other equation to find the time. So we say final velocity in y is equal to initial velocity in y plus gravity time. So this is the main formula that I gave you for final velocity in y. Now all we need to do is we're going to make substitutions, or we can directly isolate for delta t. This is our main objective in this moment. So let's analyze. Initial velocity in y here, it has an invisible symbol positive over here because this term is adding. So if you want to get rid of it, you will send it to the other side of the equation by doing a subtraction. So you will have final velocity in y minus initial velocity in y equals gravity times delta t. All I did was I removed initial velocity from here to the other side. It was adding, it came to the other side to subtract. Okay? And then this gravity, because remember, I need to leave my time alone. So this gravity is here multiplying the time. So when you isolate, you will send it to the other side of the equation to divide. So in the end, this equation is going to be transformed into final velocity in y minus initial velocity in y divided by gravity. All this is equal to delta t. And you don't see the update of the whiteboard because, you know, life happens. The internet connection is not the very best. Okay. Okay, finally. Okay, so this isolation that I did, you can keep it there in your flashcard because this is a very useful isolation for time, okay? Anytime you have the velocities, the initial velocities, you can find the time, okay? So you have initial final velocity minus initial velocity, vertical both, divided by the time. So all we need to do now is we make a substitution with the givens that we have. So we say that time is equal to final velocity in y is the one that we got from the step before. Okay, so this final velocity in y, you will replace it here. It is 21.55 meters per second. But remember, it was negative because it was going downward. This negative is from the formula. Now the initial velocity in y. The initial velocity in y is negative. If you remember, initial velocity in y is this one, and it gave us negative 8.49. So I'm going to replace it here. Negative 8.49 meters per second. And as you can see, we have minus and minus over here. So you know that whenever we have a minus and minus, it's going to turn into a positive symbol. Now all this is divided by the value of the gravity. The value of the gravity, that is negative 9.81 meters per second squared. Okay, now this equation was transformed into negative 21.55 meters per second plus minus and minus became plus 8.49 meters per second. All this divided by the gravity. How much you get from this subtraction?
13.06.
13.06. meters per second divided by the gravity, that is negative 9.81 meters per second square. So you cancel meters with meters and seconds with one of the seconds, and you will also cancel the negatives with the negatives, okay? As I told you, remember I told you, if one symbol is incorrect, that time is gonna give you negative, and nobody wants that. So we need to be careful here. How much we get as a time?
1.33 seconds.
1.33 seconds. Positive, right? Because the time can never be negative. And this is a breaking point where you are doing a quiz, you know? You have a negative time, oh, you know you did something wrong and you have to go back and see. Now, after we have the time, remember what we need to see? Remember what we are looking for, the final position in X, the final position of the stone, and then we need to make the analysis because the target is 13 meters away, okay? So now that we have the time, we can actually apply the formula to find delta X. And what is delta X? Is initial velocity times delta T. Initial velocity in X times delta T. That's the formula I gave you, okay? So the next formula is, the next step is, I think step number 4. And is we're going to find the delta X of the stone, okay? Actually, the final position of the stone, okay? So we say delta X is equal to initial velocity in X times delta T. The initial velocity in X is the one that we got from the step 1. Initial velocity in X is positive 8.49. So we replace it here. And we say delta X equals to initial velocity in X, 8.49, and this value is positive meters per second. And then we multiply times the time that we just got in the step before, that is 1.33 seconds. Here, seconds and seconds are canceled out. And we get how much?
11.29 meters.
11.29 meters. Okay, now from this, we are going to write the definition of delta X. Delta X is final position minus initial position. Okay, that is the definition of delta X. Final minus initial. Okay, and I'm looking for the final position. So that means that this initial position is gonna go to the other side. It was subtracting, it goes to the other side to add. Ephraim?
Miss, I have a question. We will do a classwork about this topic, right? Not a quiz.
Yes, we're gonna do a classwork of this topic or homework. It depends on how much time I take to explain one more example and how much time you take to do the classwork. Because this topic requires time. That's why. And we only have like 2 hours in a row and etc. Okay. So X initial is subtracting, it goes to the other side to add. So we're going to have the final position of the stone to be 11.29 meters plus the initial position. The initial position, we say that given, okay? And the initial position is 0. But it's important that you know that some other times the initial position can be different than 0, okay? So in this case, it's not going to affect the answer that we got. So the final position of the stone is equal to 11.29 meters plus 0, that is going to give you Okay, x initial is 0, okay? So it's gonna give you the same answer as the delta x. Now, what do we have to do after? We need to tell if the stone is going to hit the block. So to do that, I'm gonna bring the picture one more time. Okay. Tell me, guys, tell me. If the stone going to hit the target, is going to hit the block. So more or less, the stone moved in this direction. In the end, more or less, the stone moved in this direction.
No, it will not hit it.
More or less, the stone reached a distance of only 11.29 meters. So this is the analysis that you do, okay? It's not only just to get an answer. No, Valeria.
Miss, all that formulas we need to learn, Miss.
No, Valeria, in this case, I will allow you to bring the formulas in a flashcard, but they need to be very clean, okay? So you write all those formulas in a flashcard. Montserrat.
Miss, the gravity is always going to be on Earth, or you're going to put in other examples of Mars, or
Most of the examples are going to be based on the idea that we are on Earth, but there are some other examples that could involve a different gravity, for example, on the moon's surface or something like that. So in that case, the gravity is going to be specified in the problem. So the stone only reached a distance of 11.29 meters, which means that it's not going to hit the target. It does not hit the target. Remember, in the end, it's not just an answer. We need to analyze what we